Okay. All right. So we talked about this last time, this notion of discrete time functions, right? So that thing on the top, x of t, 5 minus 5 e to the negative t over 0.1. This form here in general is, 5 minus 5 e to the negative t over tau. What do we call tau? What's the name we give to it? Well, time. Yeah, it controls how fast the transient decays. And we use that term because usually it relates to the parameters of the circuit. Like in an RC circuit, it's R times C, right? In an LR circuit, it's L over R always. That's for us, that's not particularly important, but it is true. So we talked about this concept of if I plotted that function, the x-axis is t, the y-axis is x of t. So it's a function, right? So x of t is a function. It's a function of what? This is important, right? The discrete time function is the thing on the bottom. The continuous time function is the thing on the top, right? What is the difference here? The discrete time versus the continuous time. What's the difference between those two expressions? Because, okay, what we said is when I go and plot these things in MATLAB, right? MATLAB basically plots this, which is what? A series of points, right? What's going on with t? Why can a computer never plot this? We have a number of points. So t, x of t is a real variable. It's a function of a real variable. What does that mean? Big word. Function of a real variable means that it's a real number that's going into it. I cannot go into the computer and solve how many numbers are there between t equals 0 and t equals 1? Real numbers, there's infinitely many, right? I can't do that. So I got to approximate it. So if I wanted to plot this function from 0 to 1 second, what I do instead is I plot it at a couple of points between 0 and 1 second. And the thing I have to be smart about, I said, is the time step, the delta t, right? The way that I choose those points. And this notion of a discrete time variable, what I'm doing here is I'm saying the continuous function, it's a function of a real variable t, whereas the discrete time thing is a function of an integer variable n, right? So what do I mean when I say an integer variable n? What does that mean? What does it mean to say I have an integer variable versus a real variable? Well, t is a real number, right? It's a number that can take any real value. So it's a real variable. What about the integer variable n? What values can n take? Variables, what values do you think n can take if I say it's an integer variable? Integer? Only integers, right? Which makes sense in a computer, right? So basically what I can say is that this discrete time function, x of n, is going to basically be a series of points that lives in an array somewhere. And the first entry in the array would be x of 0. What would be the second entry in the array? So the first one, if I had that array, right, I would have x of 0 is the first entry. What's the second entry? X of 1. The third entry would be x of 2, right? I can't have x of t as an array. So what we did is we said we quote unquote discretized it, where I choose a time step delta t, and that time step tells me how much space there is on the time axis between individual points. Right. So what we did to show this is those two functions right there. So the top is the original continuous time function. The bottom is this discrete time function. All right. What's the difference here if I look at the x-axis? They look the same, right? When I look at the two on the y-axis. Right? If you didn't know any better and you looked at those two things, you would say they're the same. What's the difference there? What's that? Well, the functions themselves, okay, the functions themselves are the same on the y-axis. You're saying this is 1,000 times bigger here. That's right. Basically, what I'm plotting here is the sample number. What I'm plotting on the top is the time. Okay. So in this particular case, I think what I chose is delta t equals 0.01, I think is what I chose. Maybe it's 0.001. I don't remember. But I chose a delta t that is that value. So both of these things effectively show x of t. What I've done is I've given meaning to them on the x-axis when I drew the top plot. What did I do in the bottom plot, say versus sample number? What did I do differently when I made this plot?
Number of samples you have after you distribute that.
Yeah, basically it's saying the first entry in the array is here. Second entry in the array is here. The third entry in the array is here. The fourth is there. The fifth, I just didn't give any meaning to this. Actually, what I did here was to plot this one, I made a t vector and I said plot t comma x. And for this one, I did plot x. Right? So it just plotted all the points in order. It only gives meaning to the x-axis if you tell it to give it. I could, and you can give it the wrong meaning. I can give it the wrong t vector. You can give it the wrong t vector as long as the t vector I give it has the same number of points as the x vector. It'll plot it, right? It may not make any sense, but it'll plot it as long as it's got the same number of points. That's the only thing MATLAB's checking before it actually makes. It has no idea what you're thinking that you want it to look like, right? The job is always for you to think about what it should look like. Right? As long as you give MATLAB something that checks the syntax, it's going to gladly do it, as with any programming language. Right? All it cares about is whether you match the syntax, not whether or not it makes sense. I guarantee for problems 3 and 4 on the project, a lot of you, more than half of you, are going to make some really dumb choices at some point because you're not going to think about what the output's going to be. And you're going to get a blue screen of death sort of thing. Right? I made that point at the beginning of the semester, and I'll keep making it over the next couple of weeks. You got to think about what the output's going to be, or else there is the chance of that blue screen of death. Because you're basically trying to tell it to make a million by a million matrix or something like that, and it's choking. All right. So this concept is important. If I can get things into the computer as these samples, all right, and in reality, samples come from an analog to digital converter, like in your audio files, right? Those things came from an analog to digital converter. If I bring things into discrete time like this, I can do digital filtering, which is a much better way of doing things typically than an analog. Okay. All right. So we talked about how to discretize functions, and I basically, so in other words, how to convert them from continuous time to discrete time, and I used basically Newton's definition of the derivative, which somebody over there was calling Euler's method. And I think to be really specific, I believe this is the forward Euler's method, and there's a backward Euler's method, right? So what do you think the backward Euler's method would be? Not integration. Good guess, though. I see where you could make that guess. How else could I have written that? There's a couple of ways I could write that derivative. What's the other way that you could actually write this limit? There's probably infinitely many ways you could write it, but there's one other common one. Yeah, I could say y of t minus y of t minus delta t all over delta t. Technically, that's the same thing. That's the backward Euler's method. If you use that, this is the forward, because basically the point I'm using is in the future as opposed to in the past. All right. And then there's other ways. You could actually say, if you wanted to, you could say y of t plus delta t over 2 minus y of t minus delta t over 2. right? So there's a couple of ways to do it. And if you get into numeric solutions of things, they talk about that a lot. Like in the world of partial differential equations, that's a common thing to worry about. We're not worried about that, right? We're going to use this one approach. All right. So what we did is we basically said, okay, if I have a differential equation that's like tau dy by dt plus y of t equals x of t, how did we use this result last time? What do I do with this? What's the key assumption that I made to use this in this numeric method? I took out the limit. Yes. So yeah. So what allows me to take out the limit? If I choose a suitably small value of delta t, right, then I can say that that dy by dt is approximately y of t plus delta t minus y of t all over delta t. This is true for a suitably small delta t. Now, I think on the project, I only have you really think about this suitably small delta t in two places. The first problem and the last problem. All right. And we're going to start an example today, which is like the first problem. All right. I'm not going to make you do it for second order. Right? But I think this is something that should make sense. So basically, what do I do with this? Well, I take this result and I say, well, if this is true, then I can make that approximately a true equal sign and plug it into here, right? So we basically said I got tau times, instead of dy by dt, I said y of t plus delta t minus y of t all over delta t plus y of t equals x of t. All right. So then what do I do? What did I do with this thing? I rearranged some stuff, and basically this is an algebra expression, right? Once I rearrange this thing, I always end up, how did I phrase it? Can't remember how I did it. So I said y of t plus delta t is equal to some constant times x of t plus some constant times y of t. All right. What does this mean in words? All right, so first of all, what I call this is a linear combination. We use that term linear a lot. What's it mean to be linear? It's a line, right? What's linear mean? If I say something's linear. A line is linear, right? Yeah, no, it's a reasonable thing.
It has one root, so.
Well, these are reasonable ways of saying it. We don't really talk about it here per se, but I talk about a system being linear or a set of equations being linear. What I think of here is this output is equal to an additive combination of two other things. That's a linear system. All right. If it's not additive, like if I had x times y, that would not be an additive combination if I multiplied those two things together. This is an additive combination of x and y. So what I'm saying here is, how did you guys use this in the last problem on the homework? You put that in a for loop, right? And what were you doing at each time you went through the for loop? You're trying to pick the next value, y of t plus delta. And so the way we did this kind of in the discrete time, right, is I basically said I use the value now for the input and the value now for the output to figure out the value at the next time step. Or in discrete time, you say y of n plus 1, the next value in the array, is equal to some additive combination of the current value of the input plus the current value of the output. Okay. And at some level, this is actually kind of a more useful way of understanding what a differential equation is really doing. I always said that the output has two pieces, right? Output is a transient and steady state. The steady state, I said, always comes from the input. The transient always comes from the fact that the output changes slowly. So eventually, these two things, y of n plus 1 and y of n, should become equal to each other. All right. Let me not say too much more about that. All right. I think you should, whether you fully appreciate it or not, I think you should be able to understand this. This is something that's relatively easy to solve for in a for loop. Okay? All right. So the question becomes, what do I do if I have this thing? I have a second order equation. What should I do here? Any thoughts? How can I think of the derivative here? The second derivative. What's another way to think of a second derivative? Derivative done twice. So I can say I've got d by dt of dy by dt plus b times dy by dt plus cy t equals x of t. All right, let me call this, let me just be clear, this is y of t. Okay. So all I've done is to basically say I'm taking the derivative of the derivative, right? The second derivative is the first derivative of the first derivative. All right, so here's what I'm going to do. Is I'm gonna make a definition here. I'm gonna say let's define two things. Let's create a variable y1, which is equal to y of t. Okay. And then let's create another variable, y2. And this example, these are in the book. It's, I forget what section, 7.4, I think they go through the same thing. Right? I'm just going to define these two things. So let y1 equal y and y2 equal the first derivative of y. Okay. All right. So how do I use that here? How can I write this equation right here using that? Okay, so you're noting that y2 equals the derivative, right? So I can say that this is right here, this is y2 of t, right? This is y2 of t, like that. So I can say I've got d by dt y2 of t, right? So I just made a substitution plus b times y2 of t plus c times, so y is y1. Let me get that. All right. Now, this here is fairly easy to approach now using that definition of the derivative, right? This is one equation, but there's another equation that I have. So when I do this, what am I doing? I'm basically trying to set this up into a system of equations. All right. So the other thing I have is I know that y2 from my definitions, y2 of t equals dy by dt, or as I defined it there, dy1 by dt. Okay. All right. I'm going to break this up here in a second, but does it make sense what I did here? All I did was some substitutions. I made definitions up, and I basically used those definitions to rewrite these two equations like that. All I did. Now, how do I get rid of the derivatives? So in this one, I've got a dy2 by dt. In this one, I have a dy1 by dt. How do I get rid of those things? How do I get rid of the derivatives? and turn it into discrete time. In other words, how do I start taking the numeric approach? What do we do to take the numeric approach when I had a first derivative? I'm going to go slow to make sure it makes sense what I did. I use basically that assumption that the derivative, so I go back to the definition of the derivative. I make the assumption that delta t is suitably small that I can just replace the derivatives with this. Now, I'm not going to do the derivation because I'm going to lose you guys in this, but basically what I have written out, so all I did here was I took these two equations right here, right? And I rearranged them to look like this. Okay. I rearranged them to look like that. Then what do? Basically, I'm going to turn this into, so dy2 by dt. So if I know that dy by dt is approximately y of t plus delta t minus y of t all over delta t. What can I do here with this? How do I use this result in the first expression? Wouldn't I say y2 of t plus delta t minus what? I'm taking this side of the equation. What do I put there? But I'm using this and I'm applying it to this term. What do I write there? Yep. So y2 of t plus delta. So I'm using it for y2. So y2 of t plus delta t minus y2 of t all over delta t equals, I just say the rest of this stuff, x of t minus b y2 of t minus c y1 of t. Where b and c basically fit my terms in that differential equation. Okay. All right. I could do the same thing for this guy, right? What would I do for this one? What would I do with the dy1 by dt? How would I write that? Yeah, y1 of what? Yep, t plus delta t minus y1 of t, just using this result up here, all over delta t equals y2. Now, if I do a bunch of algebra, I basically get this. Right? And you can go through the algebra. All right. What is this? All right. It's a system of two equations. But just like we had in the other case, right, where I did first order. Basically, so the way I think about this is at t, I always know at time t, I always know the input. I always know y1, and I always know y2. So I know those things, and I can say at t plus delta t, I solve for the outputs y1 of t plus delta t and y2 of t plus delta t. So if I know these things, basically what I have here is a system of equations, right? And so how would I write out that system of equations? How would I write that out? Now, if I look at this carefully, right, I can basically say, and I don't want to write that out as a matrix. I could write that as a matrix, but you don't need to know it as a matrix. Two equations, there's two unknowns, right? At any given time step, t, I know x, I know y1, and I know y2. In other words, I know everything on this side of the equation. And then I'm solving for everything on that side of the equation. So I solve for these values, knowing these values, right? So I know everything on this, the right side, and I solve for everything on the left side, right? That's basic. So you just iterate just like you would in the first order. All right. So, what I want to do is I want to do an example then, right? So let's say I have this thing right here, right? So d squared y by dt squared plus 4 dy by dt plus 100y equals u of t. All right. And what are those two things over there? Y of 0 equals 3, y prime of 0 equals 0. What is that? What are those? Just some crap that I added. Those are my initial conditions. Why two? Why two initial conditions? Second order system, right? Second order system, I need two initial conditions. So if it was a 15th order system, how many would I need? 15, right? As it turns out, once you get to a third order system or a fourth order system, pretty much everything looks first order or second order, even if it gets to be 15. All right. Usually you can approximate it as either first or second. That's why we only ever learn anything about first and second order systems. And we don't need to know anything beyond that, really. All right. All right. We don't need to focus on that. That's something that you learn with time. All right. So I got this result here. So I want to put this guy into discrete time. So to do that, I just got to go back to my result that I had right here. So, all right, what I said was I made this definition. I said, well, let y1 of t be equal to y of t, and let y2 of t be the derivative of that. All right. And then I discretize everything. And I can go through that whole process. But if I do, basically what I'm going to end up with is y1 of t plus delta t equals y1 of t plus delta t times y2 of t, and y2 of t plus delta t equals x of t minus b y2 of t minus c y1 of t times delta t plus y2 of t. A lot of crap going on. But how do I use this? How would I use this to actually try to solve this thing? Well, I know B and I know C over here, right? And I know X, right? So the things here, so X, B, C, I know all those. What am I saying for this thing? So this whole thing is equal to U of T. All right, what's that mean? This is equal to, for T greater than or equal to 0, what's this thing equal to? 1. All right, it's equal to 1 for T greater than or equal to 0. Okay. All right. So that means for every value of X, I know that's equal to 1. Okay. What about B and C in this equation? What are they? This is just pattern matching. Hopefully it's not too bad. What do I put for B and C? What's B? If this is my expression here. Yep, B is 1. Well, no, B's not 1. It's 4. What's C? 100. Okay. Now, with this, I can write a for loop. We're going to write the for loop in a second. What else do I need to choose? There's one other variable over here that I know, but to know it, I need to choose it. What thing do I need to choose over here? Delta T. All right, so I want to think about how I create the delta T. So basically to approach these things, I got 2 steps. I did the first step, create the discretized equations, did it, all right? The second step, the hard step, is choosing the appropriate time step. All right, choosing the appropriate time step. So let's just think about this for a second. I wrote some more bullets there, but let's just think about them. What is this guy going to look like? What is y of t going to look like? Right, so second order differential equation. All differential equations, the result, the output, has two parts. What are the two parts? Always. The what and the what? No. The transient and the steady state. All right. What is the steady state here? It's a constant. I don't think it'll be U of t. I think it'll be 1/100 U of t. Right? Why do I know that? First of all, my input is a constant U of t. It's a constant 1 after t equals 0. So if my input is a constant, what's my output always have to be? Constant. Right? So I just got to choose the right. So we use that undetermined coefficient. So well, I know it's constant. And then I basically plug that unknown constant into it and solve for that unknown constant. If I did that here, right? So let's actually do it. Did I leave myself a place to? I didn't. All right, let's do it here. What would that constant be? So I guess, I say, well, let the particular solution be B, some unknown value. What's the second derivative of a constant? 0. What's the first derivative of a constant? 0. So basically I get 100 times B equals 1. So B equals 1/100. All right. The steady state solution, not interesting here, right? It's just a constant. What about the transient response? What's the transient response going to be? What is the transient response always? Always, always. Exponentials, right? Exponentials, right? And so if I have second order, how many exponentials? Go ahead. 2, right? The problem is those exponentials can have complex coefficients, right? So in general, this guy would be C, the transient response would be C1 e to the S1t plus C2 e to the S2t. And I've already said there's 4 options that can take, depending on what the values of S1 and S2 are. So those can become basically a decaying cosine wave, right? What causes that to become a decaying cosine wave? What causes this to simplify to a decaying cosine wave? What would S1 and S2 have to be? Complex numbers, right? What do we call that when they were complex numbers, those roots? S1 and S2? Underdamped, right? Basically, underdamped means that my transient response is a sine wave whose amplitude decays over time. Okay. All right. So how do I determine which one it is? Underdamped, overdamped, critically damped? Square roots of what? Right. So I go to the characteristic equation for this thing, right? So what's the characteristic equation for this guy? Okay, S squared plus 4S plus 100 equals 0. Now I'm going to solve for the roots, but how can I check whether the roots are real or complex? Yeah, discriminant part. Basically, the B squared minus 4 times C. So in this case, B squared is 16 minus 4 times 100. All right. I don't want to, it's not hard to calculate, but what is that? Less than or greater than 0? Less than or less than 0. So in that whole opposite of B plus minus square root of B squared minus 4AC all over 2A, which in this case, A is 1. All right. In this case, that means that I'm taking a square root of a negative number. That's imaginary, right? So if that's the case, then I know this thing's going to have complex roots. And as a result, it's going to be a decaying cosine wave. All right. So basically, what that means in this particular case is that my response looks like this. I don't even give a crap really per se what I know that I have a constant for my steady state. I don't really care that it's 1/100, right? I don't even care what this magnitude of C1 is. I don't care what this is. I don't care what that is. All right. What I know is that my response looks like this. All right, it's got a decaying cosine. So let me just, in words, when I say it looks like a decaying cosine, what does that mean? What does it mean to say I have a decaying cosine?
I don't find that the amplitude.
Yeah, the amplitude of this thing is being multiplied by e to the negative t over that. So in other words, you get these come on decaying over time. All right, so I had MATLAB tell me what are S1 and S2. All right, those are S1 and S2. All right, so real quick, this guy would be a constant. So we said the steady state was 1/100 plus 2 times whatever the magnitude of C1 is. I don't know what it is, and I don't care. All right. E to the negative sigma t, e to the sigma t, cosine omega d. Now, I would not expect you to know off the top of your head how I made all those jumps. Or that when I have this, I call that sigma plus j omega d, like that. So what's, back into my expression here, what's sigma and what's omega d? Oh, okay. Just give me a number based on this. The roots that I get have this form, sigma plus j omega d. So what's the number for sigma? What's the number for omega d? Sigma is -2. Okay. And omega d is what? 9.798. Right. So basically this guy is 2 magnitude of C1. Now, why am I not caring about the amplitude? Why am I caring not about the amplitude, but more about the frequency in this guy here? Do you think? Why am I caring more about those values and not so much about, say, this value or this value? Transit's only for a short period of time. And the key thing is this guy here, depending on how quickly he decays, depending on how fast that e to the negative 2t drops, that controls what the transient response looks like in time. In other words, that's going to control potentially my time step. Omega d might control my time step as well, because what is that? That's a frequency, right? A frequency means how many times do I repeat in a second. So two things that control the timing are the frequency and how fast this thing decays. Now the question is, which one matters more? Because we said, all right, what was the key thing? I'm discretizing this. What was the whole key thing about converting this thing over to a discrete time thing? I had to choose my delta t. And what did we say about my delta t? What do I need to choose about my delta t? So I needed to choose it so that it was small enough that this here, this approximation is good, right? So I need to choose it small enough. I don't need to be like Newton and say, well, the limit is delta t goes to 0. I'm going to choose it as whatever is small enough that it's basically so tiny that when I approximate this thing, it looks almost as good as the real thing. Okay? The question is, how would I choose that? Well, I have to be able to capture the smallest feature of this thing. All right, so when I look at this here, I basically said, all right, well, to determine the appropriate time step, I need to see how this guy unfolds as time advances. See how it unfolds in what I call the time domain. Right? So I look at what the transient response looks like, and I look at what the steady state looks like. So in this case, in the transient response, the steady state is boring. The steady state's constant. Okay. What can my time step be if I only needed to plot the steady state response? I would just need 2 points that could be infinitely spaced apart from each other, right? Because I'm just going to draw a flat line. I could have a value at t equal to 0 and a value at t equal to 1 billion years from now, and just draw a straight line between those 2 points. My delta t could be huge, right? But I need to choose my delta t small enough to be able to capture that whole transient response. So what I'm doing here is I'm looking at this and I'm saying there's 2 things that control that. One is this guy, and one is this frequency. So how can I think through how I choose those time steps. Any ideas? All right, so I want to try to be consistent with what I did here. So I said e to the negative t over tau. So e to the negative 2t. This term right here, this can be rewritten as 2 magnitude C1 e to the negative t over 1/2 times cosine of 9.798t plus angle C1, like that. Right? See what I did there? Yeah, that would be equal to each other. Negative t over 1/2 is the same as e to the negative 2t. Right? Because I just 1 over 1/2 is 2. Okay, so how do I make a choice now between those things? All right, so let's take a look at this. So I have basically two different things at play. I got this guy and I got this guy. Both of those things are changing over time. So if I want to see an exponential, if I just think about an exponential, if I want to draw a graph of an exponential, how long does it take for an exponential to decay and go away? 5 time constants. So we're going to use an engineering term here. I want to choose delta t much, much less than. So we say much, much less than. That's a common term we use in engineering. Math guys don't like that, right? I say much, much less than. What's much, much less than mean? Well, we're going to determine that. Delta t has to be much, much smaller than 5 tau. Because if it's much, much smaller than 5 tau, I'll see the whole exponential and I'll see it looking very exponential, right? In other words, the distance between the points in my graph is much, much smaller than the length of the entire meaningful part of the graph. All right. Well, all right. Well, so how would I, so give meaning to much, much less than? What's much, much? So if I told you I have the number 5, what's much, much less than 5? Is 4 much, much less than 5? I don't know. It's a very imprecise definition. It's not, right? Usually we say, well, if it's at least a factor of 10, maybe a factor of 100 smaller, that's much, much less than. Right? If it's a factor of 100, that's basically meaning it's like 1% of it. Right? So why don't I'll just choose arbitrarily in this case. Let's say I choose delta t to be less than or equal to 5 tau divided by 100. Right? Let's just say that's what I choose. Right? I could choose 1,000 if I wanted to. Right? Choose 10,000 if I wanted to. Right? I could choose 1/2 if I wanted to. That would be a bad choice. All right. So I want to choose something so that I know, in this case, what it's saying in words, the way I think of this is delta t is 1% of 5 tau. Right? So that's a small amount. Okay. This is where, the reason we use terms like this is because in the real world, when you're really doing real problems, you have to use what we call engineering judgment, right? As opposed to just, giving you problems and telling you here's the numbers to put in there. In the real world, I have to use some judgment about what to do. Right? So that's what we're trying to do here. So figure out how we can apply some judgment. All right. So basically what I can do is I can say, well, my tau in this case, we said was 0.5. My omega d, which how can I turn that omega d into a period? Right? Because that cosine omega dt plus some angle. How do I relate that to a period? If I have an omega, how do I relate it to a period? 2 pi over the period, t sub d. All right, so the timing fact thing here, if I want to see one period of that sine wave, and I want to see one period of that sine wave nicely, then I should say my delta t is what? How would I write some constraint for that? Delta t should be much, much less than what? If I want to see one period nicely. In other words, I want to see the cosine do its thing. I want to see the hills and valleys. How do you think I should choose it? Delta t much, much less than what? So here I said my delta t should be much, much less than the length of the whole thing. That's basically where the action's happening. So we're saying when I'm looking at this exponential, Exponential does that. So this time period here is 5 tau. And I want to choose my delta t to be much, much less than that. So in this case, I'm saying cosine looks like this, right? And I want to capture that whole thing. So I want to make sure I capture a whole period properly. So I want my time step to be much, much less than the period. Okay. So how can I choose delta t in this case? How could I choose that? Say what? Yeah. So I'll say, well, what if I choose delta t to be much less than the period, or less than or equal to the period divided by 100? Okay. Two reasonable choices. Now, when I do this, that's these two numbers, there's almost no chance those two numbers are going to be the same. Right? Let's plug in some numbers here. So what's my tau? My tau was 0.5. So I plug in 5 times 0.5 divided by 100. So I get the, looking at just the exponential, if I want to capture the exponential using this approach, my delta t should be less than or equal to 0.025 seconds. Okay. If I chose that, then the exponential would look great to me. What about for the cosine? To see the cosine, if I plug in the period, so if I plug in with my omega d, which was 9.798, 9.798, and solve for my t sub d, this would be 0.6413 seconds. So if I plug that in here, so 0.6413 divided by 100, what would that be in seconds? Yeah, 0.006413 seconds. Okay, so this says my delta t has to be less than 0.025 and less than that. So which one should I choose? The smaller. The smaller. If I choose this one, I'm not going to capture that cosine part properly. So in this case, what I'm going to do is the choice that I'm going to make is this. Now, in the project, you're not going to have a situation where I ask you to do this choosing for a second order. Now, you will have one, and we'll do this example probably on Thursday, where I have to choose between the features of the steady state and the features of the transient. All right, so you will have to choose between two things. You always choose the smaller of the two so that you see all the time domain features properly. All right, so what do? I write code at this point. All right, so those are the two equations that we wrote. And what did I actually choose for my delta t here? All right, I chose t sub d over 100. All right, so my delta t was 0.006413 seconds. All right, so let's take a look at my code here. So I got a bunch of setup up here. I'm clearing variables, I'm putting in constants, stuff like that. You guys don't like to do that. You guys like to put hard-coded numbers into stuff, and that's fine. You really want to get comfortable probably doing this, because what I like about this is I can look at the equations I have, and they look exactly like these equations, right? The equations that I'm writing down in my fancy script over here match the stuff that I have in the code, right? And that it's a lot easier for me to debug when I can match those things together, and then I can just in one place say, oh, B equals that, C equals that, right? Rather than having potentially multiple places where I hard-coded the numbers in, right? So that does help, and you want to get used to that. Okay. So what am I doing here? This is the key thing. What's all this stuff? Well, so this part right here, what is that? Yeah, so y1 and y2 are zeros, x is equal to ones. What is that? What's the code term for that?
You're initializing.
I'm initializing. I'm initializing my variables. I'm creating those variables y1, y2, and x. They're arrays, basically. And I'm initializing. X is, so one's size of t, what's the output of that? If I run that function, one's size of t, what would come from that?
For vector ones defined z.
Yeah, a vector that's all ones, or really a matrix of ones that has the size of t. But in this case, t is a, what is that? 0, colon, delta t, colon, it says 8 times tau. What is that, a row vector or a column vector? It's a row vector. So that means that I get a row vector of ones. And then y1 and y2 are a row vector of zeros. Okay, so this is me initializing stuff. What's this? What am I doing here? I got a for loop. Just like the for loop I did when I did it for the first order system. What's in my for loop? What's this? If n equals 1.
This is the first case.
Yeah, so what do you mean by first case?
Since you're always.
It's the very first time I go into the for loop, right? Very first time I go into the for loop, I load up the first entry is basically set to the initial conditions, right? So I'm loading the initial conditions into the first value. And then the first time around, do I execute this code? So as I go through the loop, so n will equal 1, I go through the loop. And then n equals 2, and I go through the loop. And then n equals 3, and I go through the loop. Do I execute this code the first time I go through? Mm-hmm. Yes. Why yes? There's no else. I don't have to have this, right? So it's going to say if n equals 1, yeah, do this, and then n. Right, so that n ends that if. So it goes to here, and then it does this, and then it does that. There's no else, so it basically does it. So basically, the first time it goes through, it loads up a value in the first entry of the array, and it loads in the second value of the array. Now, why does this stop at the length of t minus 1? We talked about this in the first order example. I'm always, every time for when n equals 1, I'm solving for n equals 2. Right? And so if I went from 1 to 1, the length of t, it's going to go doop, 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 doop. It's going to go along, fine, going to go along fine until we're in. Once it gets to the last point and it tries to load in the next value, it's like, oh, there is no other value because you created something that was the length of t. And you're trying to push something into the spot that is the length of t plus 1. It doesn't have that initial. All right. That's an error that you're going to see in your project. Many of you will see that error as you go through your project. You want to think carefully about it. In other words, remember, code is always right. Okay. You're wrong, but your code's always right. And that's important. That sounds stupid, right? But it's true. Because what it means is like that blue screen of death thing. If you and you're going to see this, I guarantee you half of you are going to get into a situation because those files that I give you, I said I give you audio files to play. They're big, right? There's several seconds of audio, right? So when you try to manipulate those things, if you screw something up, you can suddenly start making matrices when you thought you had vectors. You want to think before you execute the code about what the result is going to be. All right. That's not something you guys aren't used to thinking about what code does, right? But especially if you're a computer engineer, I always try to hammer that in. If you're a computer engineer and you make firmware, you want to think about the output of your code is going to do. What's firmware? I say firmware instructions. Well, yeah, firmware is instructions, but it's typically for some real device. Like one thing I've done in the past with my company is we did firmware for solar inverters. So basically something that's meant to process a couple hundred watts. And if I screw up the code, it just blows up the hardware, right? The computer guys, they never care. Oh, whatever, I'll fix it again. But putting the wrong thing in can be problematic. So you want to get used to thinking about what is it that I expect the output to be, all right? It's one of those things I know most of you guys aren't listening when I say that, right? But you're going to lose some of you will lose a couple of hours in the process of what's going on with this thing. It looks totally right, but your logic, something's a little bit off. And oftentimes it comes in because you haven't thought about what's the dimensions of that array. All right, be really careful about that. The common thing is when somebody goes to plot something. All of these things are either row vectors or column vectors. If you go to plot a matrix, and let's say that matrix has 20,000 by 20,000, it's going to try to make 20,000 different graphs. Right? So it's going to try to open basically 20,000 windows on your computer to make the graph. Nuts, right? That's where you get the blue screen of death stuff, right? So one thing real quick. That's what this result is supposed to look like, right? So when I run this code, that's a nice underdamped guy, right? What happens if I choose my delta T too big? Well, previously I showed you the first order just looked wrong, right? It looked like stuff was missing. This is what I did in this case. So I chose it to be too big. What happened here? It looks like it's exponentially growing. This is a real thing. If I quote unquote undersample something, I can cause the simulation to show me something that's completely absurd and couldn't happen in real life. This is sometimes called a numeric oscillation, and it can happen. Those values are real, or this can really happen in the real world, even though this can happen in the real world if you make a bad choice in a computer. The real system represented by a differential equation would never do this. But when you put it in the computer, it could if your choice for the delta T is wrong. All right. So the important thing on this was how to do the second order stuff, right? Which is basically a matter of kind of playing with these equations. Now, the thing that we need to do next time is we actually want to go through and look at an example. So this circuit that I show here, this is not the same circuit, but it's similar to the circuit that I showed you earlier. All right, so I'll post the project. My recommendation to you is between when I post the project later today and Thursday, look at problem 1. Because I'm going to do a problem that's exactly like problem 1. In fact, so exactly like it, it uses this circuit, and it's the same problem. All right, and I'll walk through that with you. All right, that doesn't mean that it'll be easy. Right, but at least it's what you it's exactly like what you're being asked to do. All right, so I'll stop there.